following Python code snippet consists of import statements importing a range of commonly utilized libraries and modules for tasks related to machine learning and data analysis. 1. NumPy for handling arrays and numerical operations. 2. Pandas for analyzing and manipulating data. 3. Matplotlib, pyplot for visualizing data. 4. Random for generating random numbers. 5. Dequeue for creating double-ended queues. 6. Sys for system-specific parameters and functions. 7. Math for mathematical operations. 8. Keras for constructing and training neural network models. 9. Load model from Keras, models for loading saved Keras models. 10. DM for incorporating progress bars into loops to monitor task progression. These libraries hold widespread application in diverse machine learning and data analysis endeavors due to their effective tools and capabilities for data manipulation, model development, result visualization, and progress tracking during training or analysis. Through the utilization of these libraries, developers and data scientists can access pre-existing functions and classes to enhance efficiency, thereby allowing them to concentrate on their primary tasks without the need to start everything from scratch. Utilizing the TensorFlow library, this code snippet aims to enable GPU memory growth, ensuring efficient memory utilization. The script begins by importing crucial modules from the TensorFlow library, including TensorFlow, Sequential, Code Model, Dense, and Atom. Next, it fetches a roster of accessible physical GPU devices by employing TensorFlow. Config, experimental, list physical device GPU. Subsequently, it loops through each GPU device, activating memory growth with TensorFlow. Config, experimental, set memory growth device true, activating memory growth with TensorFlow. Config, experimental, set memory growth device true is vital for TensorFlow operations on a GPU. This action enables TensorFlow to allocate GPU memory as and when required, rather than attempting to allocate the entire memory at the outset. By doing so, it can help mitigate memory fragmentation and boost the overall efficiency of GPU memory consumption. In Google Colab, you can use the following code snippet to seamlessly connect your Google Drive to the Colab runtime. By executing the command drive, mountain to drive, you'll be prompted to follow a link, sign into your Google account, and grant Colab permission to reach your Google Drive. This simple process empowers you to navigate, access, and manage files directly within the Colab environment. Moreover, the subsequent actions involve navigating directories within Colab. For instance, executing os Darenten Drivme Trail Simple Deep Learning FineNet 77 Trigger alters the current directory to a specific path within the linked Google Drive. Additionally, the PuD command operates as a shell directive that displays the current working directory. By incorporating this setup, you can seamlessly interact with files, datasets, or models hosted in your Google Drive while working on a Colab notebook. This integration streamlines data accessibility and storage, fostering a convenient data flow between Google Drive and the Colab ecosystem. The following script imports data from a CT file labeled AGSP 2011. C and loads it into a pandas data frame utilizing the readc method. By specifying index all0, the initial column in the CT is designated as the data frame's index. Subsequently, the data frame's contents are exhibited post-reading. This snippet of code proves handy for converting data from a CT file into a structured form such as a data frame in Python. This, in turn, facilitates the handling, examination, and representation of the data through pandas. The below code utilizes the Matplotlib library to generate a fresh plot with custom dimensions of 15.5 inches. It proceeds to depict the AGI close values extracted from a data frame named data against the index values. Assigning the line the identifier GIST, the e-axis descriptor is defined as prices, and the title of the plot is denoted as GISTI prices. Moreover, grid lines are incorporated into the plot to facilitate data analysis. This script comes in handy when we aim to plot stock prices or other time series data. By stipulating a specific figure size, labeling the axis, providing a title for the plot, and displaying grid lines, we can elevate the plot's readability and comprehensibility. Such enhancements enable us to gain deeper insights into the data and arrive at well-founded conclusions based on the visual representation. In this script, a class named agent is defined to embody a reinforcement learning agent. Within this class, there are functions enabling the agent to engage with an environment, absorb insights from its encounters, and formulate judgments based on its learnings. To elaborate on the operations conducted by the code 1, the init function kickstarts the agent by initializing various parameters such as the state space dimensions, distinguishing between evaluation and training modes, specifying the model name, setting hyperparameters for learning, allocating memory for storing experiences, and more. Additionally, it loads a pre-existing model if operating in evaluation mode or constructs a new model for training purposes. 2. The model function establishes a neural network model utilizing keras, which the agent leverages to make decisions grounded in the input state. 3. The act function is entrusted with choosing an action based on the current state. It leverages an epsilon greedy policy to maintain a balance between exploration and exploitation. With this policy, it randomly selects an action with a probability of epsilon or opts for the most promising action foreseen by the model. 4. The explore function orchestrates experience replay for the agent. It extracts a batch of experiences from its memory bank and uses them to refine the neural network model through training. It computes the target value for each experience contingent on the accrued reward. In essence, this code encapsulates the core functionalities requisite for deploying a seek learning agent capable of interacting with an environment, imbibing knowledge from its exploits, and honing its decision-making prowess over time via the training regimen. It amalgamates neural networks, reinforcement learning strategies, and memory replay to expedite learning and decision-making processes within intricate environments. The code excerpt provided forms a segment of a broader script, presumably focusing on financial data analysis or stock market forecasting. Let's delve into the functions outlined in the code. 1. Format pre. In this function converts a numerical value n into a currency string with 2 decimal places. You can add a as a prefix if the number is negative. 2. Get stock data vecchi. In this function, stock data is read from a C file, probably containing historical stock prices. It extracts the adjusted closing values linked to a specific key and then compiles them into a list. 3. Sigmoid used to compute the sigmoid function of a given input x. This function is a common tool in machine learning and neural networks. It introduces nonlinearity into the output of models to enhance their predictive capabilities. 4. Get state data t. And this function readies the state for input into a machine learning model. It processes a list of historical stock price data, a current time index t, and a parameter in denoting the number of historical time steps to include. By computing the differences between consecutive prices, applying the sigmoid function to these variances, and presenting the outcome as a NumPy array, it prepares the data for model consumption. The likely purpose of this code segment is to format historical stock price data into a structure suitable for machine learning model input, particularly neural networks. The utilization of the sigmoid function on price differences aims to enable the model to discern patterns or trends within stock prices more effectively, aiding in analysis and prediction tasks associated with the stock market. The function fit is designed to train a reinforcement learning agent to navigate buy and sell choices in stock market trading. Below is a breakdown of the code's operation. Initially, it creates an agent instance with a set window size for data input. Then it fetches the stock price data for the specified stock name. The training procedure spans multiple episodes. Within each episode, it sets up the state, cumulative profit, and the agent stock storage. At each time step t, the agent decides on an action: buying, selling, or staying put according to the present state. If the chosen action is to buy and the agent holds no stocks, it acquires the current stock price. Alternatively, if the choice is to sell and the agent possesses stocks, it computes the reward based on price alterations, updates the total profit, and removes the stock from its possession. The agent's recollection is then updated with the experience tuple state. Action, reward, next state, done. At intervals, the agent engages in experience replay to assimilate knowledge from previously stored encounters. The model is saved every 10 episodes, and the final return of the function is the cumulative profit amassed throughout the training regimen. This script's objective is to refine a reinforcement learning agent's ability to make lucrative trading judgments based on historical price insights. The training method involves incremental learning from preceding encounters to enhance decision-making skills progressively. By automating the training process, the function streamlines the evaluation of the agent's trading acumen. In this code snippet, we have the declaration of several key variables: stock name, window size, opacity count, and batch size. The stock name variable is assigned the value hex 2011, likely denoting a specific stock symbol along with the corresponding year. Next, the window size variable is initialized to 10, an integer representing the size of a data processing or analysis window. The episode count variable is set to 50, typically indicative of the number of episodes within a machine learning training framework or a similar context. Lastly, the batch size is defined as 32, representing the quantity of data samples handled per batch during the training process. These variables play a crucial role in configuring parameters for tasks involving stock market data or related fields, aiding in effective dataset management and model optimization for enhanced learning outcomes. The code line appears to execute the function's fit by passing in arguments like stock name, window size, batch size, and episode count. The result is stored in a variable called total profits. It seems like the fit function is part of a reinforcement learning setup, potentially incorporating the e-learning algorithm for stock market transactions. This function likely takes inputs such as the stock data stock name, the window size for data analysis, the batch size for model training, and the number of episodes for training. Its aim probably involves training a e-learning agent on stock information to predict profitable trading choices. The provided code snippet is designed to automatize the training process of the e-learning model on stock data, enabling the optimization of trading strategies and the potential maximization of profits without manual input. This system permits streamlined testing of various parameters and configurations to pinpoint the most effective trading approach. The following script generates a basic line graph illustrating the progression of profits over time within a scenario structured around episodes. To begin, a figure is created with dimensions set at 15 units in width and 5 units in height using the line pult. Figure fixes in 15:5. Subsequently, the line of code pult total profits charts the content of the variable total profits along the y-axis against the index of the data points on the x-axis. A horizontal line representing the average value of total profits across all episodes is incorporated with the line pult. Linksimp, mean total profits, 0, Glen total profits. The x-axis label is designated as episodes with pult. Clibble episodes, while gains is assigned as the label for the y-axis through pult. Label gains, but plots title, evolution de gains and function de episodes translated to English as evolution of gains with respect to episodes, is set via pult, title. Finally, to enhance legibility, a grid is introduced to the plot by executing pult. Grid. This code plays a pivotal role in portraying the fluctuation of profits across episodes, offering valuable insights into gain patterns throughout the learning journey or any scenario where profit progression is monitored over time. Such visual depictions facilitate the comprehension of performance trends and profit variability. This function is designed to retrieve stock market data by utilizing a key to locate a specific file. It then reads and processes the data to generate additional values co, ultimately constructing a data frame object with the modified data using the pandas library. Here's a breakdown of the code's functionality. 1. It imports stock market data from a CV file denoted by the key value and loads it through TE. Reds. 2. The code isolates the close, high, and low columns from the dataset. 3. It computes log of high open, low log of low open, and log of close open values based on the extracted information. 4. Subsequently, a new data frame named data is generated, encompassing columns for close, low, code that encompass the calculated values. The primary objective of this code is to transform unprocessed stock market data into a structured format conducive for analysis. The refined data facilitates various analytical and modeling tasks. By encapsulating the data processing logic within the function, it enhances reusability and organizes the modified data within the variable data. This function called getState is designed to work with financial data by calculating the sigmoid of stock price differences based on the given parameters data, T and N. Essentially, the function computes the sigmoid values from a specified window of stock prices to derive meaningful features for analysis or machine learning models. To break down how the code operates, 1. Initially, it determines the variable D by subtracting N1 from T. 2. It then creates an array called rays filled with zeros having dimensions of data. Shipicon N1. 3. The function iterates through each column of the input data, constructing a data block for each column. 4. If D is not negative, it extracts a slice of data ranging from index D to T1. Otherwise, it pads the block with zeros to ensure completeness. 5. For every block, the function computes the sigmoid of consecutive price variances, saving the results in the rays array. 6. Finally, it converts the resulting array into a Python list after flattening it and returns it as output. This code snippet plays a crucial role in processing stock data by transforming price differentials into sigmoid values, facilitating feature extraction for subsequent analysis or machine learning tasks. It enhances the handling of financial time series data by extracting pertinent insights from price fluctuations, rendering it suitable for modeling purposes. This function, called fit, is designed to train a reinforcement learning agent on stock market data with the goal of developing a solid trading strategy. Here's a breakdown of its functionality in more colloquial terms to begin with. It sets up the agent with a specific state size derived from the window size provided. Next, it fetches the price data for a specified stock. Then, it kicks off a series of episodes to train the agent. The function keeps tabs on the profits earned in each episode by storing them in a list. For every episode, it establishes the initial conditions for the agent, such as the starting state, profit, and inventory. It then delves into a loop to go through each time step in the data one by one. At each step, the agent makes a decision to buy, sell, or hold based on its learned policy. It then updates its state according to the action taken and computes the reward, profit, or loss for that action. The agent's memory is updated with each experience comprising the current state, action, reward, next state, and a flag indicating if the episode is complete. The function also incorporates experience replay by sampling a batch of experiences randomly from memory to update the agent's network. When an episode concludes reaching the end of the data, the agent closes any remaining positions by selling all stocks. It logs the total profit for that episode and stores it in the list. Optionally, the model can be saved every 10 episodes. Lastly, the function returns the list of total profits obtained. This code allows us to train a reinforcement learning agent deep learning to make informed trading decisions in the stock market based on historical price data. By learning from past encounters, the agent strives to maximize profits by following the age-old adage of buying low and selling high. The training regimen involves engaging with stock market data, taking actions, receiving rewards, and fine-tuning its approach to make smarter choices as it progresses. In this snippet, we see a piece of code that initializes three variables: stock name, window size, and episode count. The variable stock name is given the string value exp 2011, typically indicating a specific stock symbol. Setting window size to 10 assigns it an integer value. Likewise, episode count is initialized as an integer, specifically 50. These variables are commonly employed in programs that deal with stock market data analysis. By storing these values in variables, it becomes simpler to refer to and modify them at various points in the code. The utilization of the int function ensures that window size and episode count hold integer values. A feature crucial for certain arithmetic operations are comparisons within the program. This line of code appears to execute a function known as fit, passing in 4 arguments: stock name, window size, batch size, and episode count. The main goal of this function is to facilitate the training of a machine learning model designed to forecast stock market returns. It is highly likely that the function ingests historical stock data alongside supplementary parameters like the window size, batch size for training purposes, and the episode count for training duration. The function employs the learning algorithm to educate a model capable of anticipating forthcoming stock prices or returns relying on the provided input parameters. Learning represents a form of reinforcement learning algorithm aiding the model in grasping the projected rewards associated with executing particular actions within a given state. When we invoke this function, essentially, we are directing the machine learning model to absorb insights from the historical stock data furnished, paving the way for predictions and profit optimization within the stock market realm. Leveraging machine learning within stock market analysis can empower investors to make more astute decisions, potentially elevating their profit margins. Utilizing the matplotlib library, this code excerpt generates a line plot illustrating the progression of total profits throughout multiple episodes. Let's dissect each segment of the code. 1. Initiating a new plot figure with dimensions specified as 15 inches in width and 5 inches in height via the line plot. Figure fixed size in 15.5.2. Displaying the total profits dataset as a line plot on the graph by executing plot. Plot total profits. 3. Incorporating a horizontal line, delineating the mean value of total profits across all episodes. Using plot, plainsimp, mean total profits, 0, blend total profits to provide a visual representation of the average profit level. 4. Assigning the x-axis label as episodes through plot, clibel episodes to denote the data presented on the horizontal axis. 5. Defining the y-axis label as gains with plot, syllable gains to describe the data depicted on the vertical axis. 6. Tailing the plot evolution to gains in function to episodes with plot. Tet evolution to gains in function to episodes translating to evolution of gains over episodes. 7. Enabling a grid on the plot by invoking plot grid to facilitate data comprehension and visualization. This code snippet proves beneficial for effectively visualizing and examining the total profits accumulated over successive episodes in a succinct and insightful manner. The inclusion of the line plot, mean line, axis labels, title, And grid enhances the transparency and readability of data representation, fostering comprehension and analysis of profit evolution over time. The function fit is crafted to train a reinforcement learning agent in stock trading through deep learning technique. The process involves to kick things off, the function sets up an agent for deep learning with a specified state size. Then, it pulls stock price data for a chosen stock, such as the SPY 500. The next step is to run through a series of episodes, each representing a complete analysis of the data. Within each episode, the data is segmented into windows of a designated size, initializing total profit and the agent's inventory. During each time step in an episode, features are generated for the current state. An action is picked using the agent's policy epsilon greedy approach. The state is updated based on the taken action. Rewards are computed according to the action executed by sell, hold, or short. The agent's memory is updated with the experience tuple. Experience replay is performed to assimilate insights from prior experiences. Upon completing all time steps within an episode, the function records specifics about the agent's inventory, computes and showcases the total profit, appending it to the profit list. The model is saved every 10 episodes. To wrap up, the function furnishes a list of the total profits garnered in each episode. This code proves instrumental in training a profound reinforcement learning model for making trading decisions grounded in historical stock price data. Leveraging deep learning, the agent can grasp a strategy that enhances its profit margins over time, empowering it to make astute choices regarding stock transactions. This tool holds significant value for algorithmic trading and financial assessments. It seems like this code utilizes a function named fit, which takes stock name, window size, batch size, and episode count as arguments. The function appears to execute a C-learning training process or a similar reinforcement learning method tailored for stock trading. Presumably, stock name denotes the dataset of the stock being analyzed, while window size signifies the observation window's dimensions and episode count indicates the quantity of learning episodes. Fit likely integrates a reinforcement learning algorithm that leverages the historical stock data and stock name to model training. Employing a C-learning approach, it navigates through the specified episode's episode count, extracting insights from each session to optimize profits through strategic decisions based on prior data. The function's output seems to be total profits, indicating the accumulated profits from this learning procedure. The code's objective seems to revolve around employing reinforcement learning strategies to train a stock data model and appraise its efficacy based on the attained profits. This code snippet serves the purpose of generating a plot illustrating the progression of profits across episodes. Let's delve into the breakdown of each segment of the code to start off. The snippet kicks things off by creating a fresh plot figure with dimensions specified as 15 units in width and 5 units in height via the line pult. Figure fixes in 15.5. Next up, the command pult. Total profits is in charge of graphing the total profits list values on the y-axis against their corresponding indices on the x-axis. Following that, bolt, plainsimp, mean total profits, 0. Len total profits is responsible for incorporating a horizontal line on the plot denoting the average value of total profits. This line spans from the Zircots index to the length of total profits. Moving on, bolt, Klebel episode sets the x-axis label as episodes. Similarly, with pult, syllable gains, the y-axis label is set as gains. Subsequently, the line pult, tit evolution de gains in function de episodes establishes the title of the plot as evolution de gains in function de episodes, translating to evolution of gains as a function of episodes. Lastly, by including pult, grid lines are introduced to the plot, enhancing readability and aiding in the interpretation of data points. In essence, this code aims to visually represent the fluctuations in profits over various episodes or time increments. The plot facilitates the comprehension of profit trends, variations, and patterns over time, emphasizing the average profit metric to offer insights into overall performance. By presenting data in this graphical format, analysts, researchers, and decision makers can leverage observed trends to make well-informed decisions. The code provided offers an implementation of an agent class tailored for maneuvering within a reinforcement learning setting. Among the attributes found in the agent class are state size, denoting the count of normalized preceding days; action size, representing the potential actions such as sit, buy, or sell; memory to cache transitions; inventory for monitoring own stocks; and parameters like epsilon for balancing exploration and exploitation; gamma for discounting, as well as a neural network model for predictive purposes. In the model method, a neural network structure is drafted utilizing keras, accepting the state size as input and yielding values for individual actions. structured through dense layers incorporating ReLU activation, culminating with linear activation in the output layer. The ACT method orchestrates action selection grounded on the present state, opting for either a random action with probability epsilon to blend exploration and exploitation or the action with the highest predicted z-value from the model. For experience replay, the XPerPlay method retrieves a mini-bath of transitions from memory, determines target's value, and hones the neural network model to minimize mean-squared error amid the anticipated and target's values. Utilizing this code is paramount in the development of a reinforcement learning agent primed to navigate the stock market using historical data. The agent refines its decision-making prowess by engaging with the environment, probing various strategies, and honing its values through experience replay to enhance decision-making acumen progressively. Here's a breakdown of how this code snippet operates. It serves as a hypothetical illustration of employing a function to train a model aimed at forecasting stock prices. Three variables, namely stock name, window size, and opacity count, receive predefined values. Specifically, stock name is assigned hex by 2011. Window size is initialized as 10 and opacity count is set at 50. Next in line, the fit function is invoked, passing stock name, window size, BAP size, and opacity count as arguments. In the context provided, it seems that fit function is utilized for instructing a model on how to forecast stock prices via reinforcement learning. Subsequently, the function embarks on training the model utilizing the designated stock dataset X by 2011, along with the specified window size, batch size, and the number of episodes for reinforcement learning. The variable named total profits is designated to retain the outcome yielded by the fit function. This result could likely represent the cumulative profits attained by the model subsequent to its training. Hence, the purpose of this code snippet is to leverage the fit function for model training with the aim of predicting stock prices using reinforcement learning alongside customized parameters. Such code snippets are particularly beneficial for traders, investors, or analysts seeking to automate or heighten their decision-making capabilities within the realm of stock trading. The provided code serves the purpose of illustrating the progression of profits throughout different episodes during a training phase. Here's a breakdown of the tasks executed by this code. Firstly, it generates a plot with specified dimensions by employing pult, figure fixes in 15. 5. Then, it displays the cumulative profits across episodes on the plot through pult. Plottable profits, a horizontal line indicating the average of the total profits, is included using pult. Cleansump, mean total profits, 0, blend total profits. To enhance readability, it designates episodes as the x-axis label with pult. Global episodes and gains as the y-axis label using pult. Tillable gains. The plot title is set as Evolution de gains and function de episodes via pult. Evolution de gains and function de episodes. Lastly, a grid is incorporated into the plot for better visual context with pult. Grid. This code proves vital for tracking training advancements, observing the fluctuations in profits per episode, recognizing patterns, and facilitating decision-making processes based on the showcase data. Visual representations like this are fundamental across diverse domains such as machine learning, finance and optimization for progress tracking, issue identification, and performance enhancements. In this script, a class called agent is outlined to portray an entity capable of deciding between sitting, buying, or selling based on the given situation, leveraging a neural network model for these determinations. The constructor designator sets up the agent with specific attributes like state size, model name, and whether it's for training or evaluation. The secluded function model establishes a neural network model with distinct layer setups using the Keras library. The ACT function assists the agent in exploring randomly or foreseeing actions based on current model forecasts. The XPerPlay mechanism comes into play for experience replay, involving the sampling of a random set of actions, rewards, states, and subsequent states to refine the model for enhanced value predictions. This class is fundamental for embedding a reinforcement learning system, notably in contexts such as stock trading or gaming, where an agent must grasp from its interactions to make sound judgments. The neural network model aids in estimating values for varied statecation combinations, empowering the agent to advance its decision-making skills progressively. This piece of code seems to be designed for calculating the overall profits produced by a trading algorithm. Assigned with the values X by 2011, 10, and 50, stock name, window size, and opacity count kick off the process. The fit function is invoked with stock name, window size, but strangely misses the definition for batch size. It's highly probable that the fit function enables the trading logic tailored for the stock denoted by stock name. likely leveraging reinforcement learning like deep learning to steer trading choices using the pertinent stock data and settings. Throughout episodic count iterations, possibly mirroring simulated trading periods or days, the function operates. Upon finishing the fit function run, the aim is to receive the total profits yielded by the trading algorithm over the specified episode count. This code snippet furnishes a means to automate the evaluation and testing of a trading algorithm with distinct stock data and parameters. By making use of functions such as fit, one can conduct simulations to gauge algorithm efficacy and juxtapose various trading approaches sans real financial jeopardy in the stock market. This piece of code employs the Matplotlib library to craft a visual depiction of the progression of total profits throughout episodes. Each line serves a specific purpose to begin with. Pult, figure fix is 15. 5 sets the dimensions of the plot at 15 units wide by 5 units high. Next, build, plot total profits illustrates the total profits variation across episodes. Following that, Pult, cleansen, mean total profits, 0, len total profits draws a horizontal line on the plot denoting the mean total profits value. Moving on, Pult, clibel episodes assigns the x-axis label as episodes. Then, Pult, syllable gains designates the y-axis label as gains. Subsequently, Pult, evolution de gains and function de episodes establishes the plot's title as evolution de gains and function de episodes. Lastly, Pult, grid enforces a grid on the plot to enhance readability. Leveraging this code proves advantageous as it generates a lucid representation of how total profits fluctuate over episodes, aiding in deciphering the data and spotting any underlying patterns. The inclusion of the mean horizontal line facilitates the observation of profit deviations from the average. Moreover, the labels and title contribute contextual information, while the grid improves the plot's coherence for easier analysis. In this snippet, the code employs the pip install command to add the eFinance library. Pip, Python's package installer, simplifies the process of installing and handling Python packages. By using the install command, pip is directed to add a package. eFinance, a Python library, facilitates the retrieval of financial information, such as stock prices, from Yahoo Finance. Executing this code results in the addition of the eFinance library. This enables you to leverage it in your Python scripts to extract financial data for analysis or other uses. It guarantees that the essential dependencies are fetched and ready within your Python setup. Utilizing the eFinance library, this script fetches historical stock price details concerning the SP 500 index X throughout the calendar year 2012 from a financial data source. This piece of code proves invaluable for individuals seeking to delve into historical stock or index prices for diverse financial purposes like analysis, modeling, or visualization in the financial realm. Access to this data empowers users to conduct a wide range of analyses, such as return calculations, volatility assessments, and the creation of visual aids for gaining deeper insights into market dynamics, hence aiding in making well-informed investment choices. It appears that SP 500 2012 is a likely reference to a variable related to the SP 500 index data for the specific year of 2012. The SP 500 is a renowned stock market index capturing the performance of 500 large US-listed companies. The inclusion of 2012 suggests a focus on data pertinent to the SP 500 index for that particular year. In handling financial data such as the SP 500 index values, programmers frequently utilize code to retrieve historical data, identify trends, generate visualizations, and conduct analyses. This practice enables them to glean insights into stock market trends, make well-informed investment choices, conduct thorough research, and produce comprehensive reports. By incorporating SP 500 2012 into their code, developers can specifically access and work with SP 500 index data from the year 2012. This capability equips them to effectively analyze and interpret financial data for enhanced decision-making processes. It seems like this code snippet kicks things off by setting up some variables with particular values. First off, the variable stock name is initialized with the ticker symbol AGSP, which stands for the SP 500 index. The variable window size is set to the integer 10, possibly indicating the size of a moving window used for analysis or forecasting. As for model name, it's given the string model TEP50, hinting at a specific model or version. On top of that, start and end are likely date strings representing the beginning and conclusion dates, respectively. Determining the exact role of these variables and how they fit into the bigger picture without looking at the entire code is a bit tricky. Typically, though, these variables are put in place to configure and customize a data analysis or prediction script, ensuring flexibility and adaptability without directly tweaking the core code. The function named getStockDataEvaluation has been created to fetch stock information using the eFinance library. It also reads a CSV file related to a specified stock symbol during a defined time frame. It then extracts important financial data points from the acquired information like closing prices on a daily basis, log returns for high divided by open, low divided by open, and close divided by open. The collected data is organized in a pandas data frame and then handed back by the function. Its primary objective is to retrieve and assess stock data pertaining to a particular stock symbol and period. This function requires three parameters: key stock symbol, start beginning date, and end ending date to acquire stock data for the set time frame and symbol. It is beneficial for conducting diverse analyses and making predictions relevant to stocks and the financial sector. The function evaluate provided below serves to assess the performance of a trading agent trading a specific stock by employing a seek learning method. The breakdown of the code functionality is as follows: 1. Initialization of the agent with a designated model. 2. Acquisition of stock data within a specified time frame from start to end. 3. Sequential processing of the stock data. 4. At each time step, the agent decides on an action depending on the existing state comprising price details, current position, and gains. 5. Subsequent to the action, whether purchasing, vending, or retaining, the agent updates its holdings and computes rewards. 6. Finally, the agent computes and presents the net profit or loss incurred during the process. This code is paramount for enacting and validating trading tactics using reinforcement learning, permitting the training of an agent to take decisions grounded on past stock prices and appraising its performance within a simulated setting. The incorporation of the key learning algorithm aids the agent in grasping the most favorable policy for trading through the maximization of cumulative rewards across time. The evaluate function appears to play a key role in assessing the performance of a reinforcement learning agent tasked with stock trading decisions. Let's delve into the details of the function's parameters. 1. Stock name. This parameter likely pinpoints the specific stock under evaluation by the agent. 2. Start. This parameter probably denotes the commencement date of the evaluation period. 3. End. This parameter presumably signifies the conclusion date of the evaluation period. 4. Window size. This parameter defines the window's dimensions for constructing the state representation, such as historical stock prices essential for the agent's training. 5. Batch size. This parameter determines the batch size utilized during the evaluation process to streamline computations. 6. Model name. This parameter is anticipated to indicate the model employed by the reinforcement learning agent, which might involve a deep neural network, learning algorithm, or another model variant. Essentially, the function likely acquires historical stock data for the specified stock name within the provided timeframe start to end. It proceeds by constructing a sliding window size to create the states from the stock data, which are utilized by the agent to inform its decisions. During the evaluation phase, the function probably scrutinizes the agent's actions against the designated model name using a batch size to boost processing efficiency. This piece of code proves invaluable in appraising the performance of an enroll agent engaged in trading a specific stock within a predefined time frame. By assessing the agent's choices, one can gauge the model's efficacy and potentially implement enhancements to bolster its performance in real-world trading scenarios.